maybe. We'll see. I don't know if I have that or not. Okay, so first of all, what's the equation of the graph? So we're going to do number 8 by popular demand. The equation of the graph. So start by looking at the midline. What's the midline? -1 is the midline. And then do we have, if we're starting at 0 there, would it be most convenient to use sine or cosine? So this would be starting at 0, we got the standard sine shape, right? Mid to max to mid to min. Mid to max to mid to min, back to mid. That's sine, right? So, and then is there a vertical stretch? Of how much? 2. So we got 2 times sine, but then the midline is down 1. And the last thing is the period of this thing. Well, what fraction is that right there of 2 pi? What fraction right there is that of 2 pi? So we're scrunched in by how many times? 3, right? Do you see that this is 1/3? This is actually what? 2 pi over 3. This period is 2 pi over 3. So we're saying, we have sine of b theta, and we know one period of the argument will be sine always has a period of 2 pi. So what is this coefficient b that gets us this to be 2 pi when we reach 2 pi over 3 for theta, right? So when theta reaches 2 pi over 3, we want that whole argument to reach 2 pi because the sine of 2 pi, that's our period. So b times 2 pi over 3. So when theta does a full cycle, we need that argument to reach 2 pi. Therefore, b is 3. Okay, so we got the equation. Just write it in here before I forget. It is 2 sine of 3 theta minus 1. Okay? And now we want to sketch it. All right, so we're going to follow the graph. I'm going to go a little bit quick, but you've worked on it, so that should be okay. And here we go. Okay, so at first it's at -1. So when theta equals 0 or at -1, where's that? Right there. So theta equals 0, -1. And then really this is about thirds, right? So this is, or sixths. So this is pi over 6, pi over 3, pi over 2. So these are the key points in this curve. The pi over 4s don't really play into it. So it's each quadrant divided up into 3. So what happens? As we go from 0 to pi over 6, we go all the way from -1 to 1, and somewhere in between there, we hit 0. So pi over 6 is this one, and we're going to make it to 1 at pi over 6. And in between, we're going to go through 0. So it's going to decrease, or excuse me, increase from -1 up to 0, and then hit 1, all from 0 as the angle goes from 0 to pi over 6. So here's increasing to 0, and then up to 1, something like that. That's just the first pi over 6. Then the next pi over 6, from pi over 6 to pi over 3, it's going to go from 1 all the way to -3 and 0 somewhere in there. Okay, so here's pi over 6. Where is -3? This is, I'm sorry, pi over 3. So from pi over 6 to pi over 3, sorry, back to -1. All right, pi pi over 6. All right, so from 0 to pi over 6, it goes from -1 to 1. And then from pi over 6 to pi over 3, it goes back to -1. So it's gonna do this and reverse, but when we get to pi over 6, now we're going to be back at -1 here. So it's going to kind of do symmetrically what it did here, but between pi over 3, pi over 6 and pi over 3. That. So now we're at pi over 3 and -1 right here. We're at this point right here. And then from pi over 3 to pi over 2, it's going to go from -1 to -3. So here we are at pi over 3, and we're going to go to pi over 2. And when we reach pi over 2, we're going to be at -3. So it's going to do that. All right, now we're at pi over 2. From pi over 2 to 2 pi over 3, that's this one, it's going to go back to -1. So 2 pi over 3 is this angle right here. -1 is right there. So it's going to go back to -1. But remember, we're in the second quadrant now. We're at this angle up here, 2 pi over 3. All right, so then from 2 pi over 3 to 5 pi over 6, it's going to head back through 0 from -1 to +1. So 5 pi over 6 is here, and we're going to make it to +1 through 0. So it's going to go like this. All right, now I'm at 5 pi over 6 and +1. That's this point right here. And then when we get to pi, okay, so then as we go from 5 pi over 6 to pi, it's going to go back from 1 to -1. So that's at pi. Here's -1. It's going to go through 0 somewhere in there, so it's going to be like this. And I'll be at pi -1. And then at 4 pi over 3, it's going to go out to -3. So 4 pi over 3 is this angle. And so -3 is here. So, 4 pi over 3. Oh, no, 7 pi over 6. So this is from pi to 7 pi over 6. It's going to go from -1 to -3. And this is 7 pi over 6 here. So I just said the wrong angle. I see. Is that right? Okay. Then from 7 pi over 6 to 4 pi over 3, it's going to go back to -1. 4 pi over 3 is this angle here. -1 on that angle would be about here. So back to -1. Okay. Then we're at, where are we? We're at 4 pi over 3. So from 4 pi over 3 to 3 pi over 2 goes from -1 to +1. So 3 pi over 2 is straight down. +1 is there. So we're going to go through 0. Come out like that. And then we're going to go from, at 3 pi over 2, we're going to go from, in the next pi over 6, we're going to go from +1 back to -1. So at this angle right here, 5 pi over 3, we're going to be at -1, which is right there. And we're going to go through 0 to do it. And then out to -3. And then back to -1 at 2 pi. 2 pi is to the right. -1 is where we started. Phew. Yeah, you picked the right one. One's hard. Let's see a pretty version of it. So any questions on that? This is going to make it look easy now. If I can get it. If you can do that one, you're in good shape. It's hard. You really have to keep track of angles and especially those negative values of r for the angles. You have to know what quadrant you're in. R is in the opposite quadrant if r is negative. Did it help? Any questions? Okay, so like I said, you've got some type of polar sketching, no calculator on the exam. You've got to know how to do these. This is really test your knowledge of the polar plane, how theta and r work, okay? It's on the final. Last chance. Okay, let's do the last web work problem that had lower success. At least when I checked it did, so let's see, make sure. Where are we at? 33? Last one. So we want to find the equation of the tangent line to the curve. Okay, equation of the tangent line to the curve. So we want to still think about that as, we're kind of thinking both in polar coordinates and rectangular coordinates. When we write a tangent line, we're going to do that thinking rectangular coordinates. But to get everything that we need, we're working in polar coordinates. So what do we need to write the equation of a line? We need rate of change, or slope, and some point x, y. So given the rate of change and a point, we all should be able to write the equation of a line through that. So using our polar knowledge of this graph at this angle, we're going to come up with the x and y coordinates of the point and the rate of change, and then form the equation of the line just like you've done in your whole career. Okay, so how are we going to get the rate of change? So this, or the slope, we know that's dy dx. And to get dy dx, we said last time, it's going to be dy d theta over dx d theta. Where does dy d theta come from? Well, y is r sine theta always, right? And x is r cosine theta. And now remember, r, for our example, r is 2 sine 2 theta. It's a function of theta. R changes with theta. That's what gives us the curve, right? As theta changes, we have different values of r. So in order to get our x and y coordinates, those r's have to be whatever r is in terms of theta, which results in us doing the product rule to get dy d theta is going to be product rule, because r is a function of theta. All right, so what is it? Derivative of the first times the second plus the first times the derivative of the second over dx d theta. Derivative of the first times the second plus the first times the derivative of the second, which is like that. So I'm just pulling the negative out. So derivative of cosine negative sine, so I'll just use it, do minus r sine theta. Okay, so we just have lots of algebra to do to get these individual derivatives and then to calculate dy dx. So where are we at pi over 6? Okay, so what is r prime? So we'll do one more. R prime is what? 4 cosine 4 theta? I think that's right. 4 cosine 2 theta, thank you. Okay, here we go. So we got a lot of math to do. We got 4 cosine of, and I'm going to plug in the pi or the 6, because we want specifically at dy dx. So 4 cosine, 2 times pi over 6, times sine times sine of pi over 6 plus 2 sine of 2 times pi over 6 cosine pi over 6. Did I get it all in there right? Over r prime, 4 cosine 2 times pi over 6 minus, or sorry, times cosine pi over 6 minus r2 sine 2 pi over 6 sine pi over 6. Okay, and cosine of, this is pi over 3, cosine of pi over 3 and sine of pi over 6 are both 1/2. So this is 4 times 1/2 times 1/2, which I think is 1. Is that right? Check it again. Cosine of pi over 3, yes, that's 1/2. Sine of pi over 6 is 1/2, so 1/2 times 1/2 times 4 is 1. Okay, this is now sine of pi over 3, cosine of pi over 6. Those are both radical 3 over 2. Radical 3 over 2 times radical 3 over 2 times 2 is 3. Check my math. Okay, now down the bottom. 4 times 1/2 times radical 3 over 2, which is radical 3. This is 1/2. This is radical 3 over 2. So 2, 2, and 4 go away. Left with radical 3, that's right. And then minus 2 times sine of pi over 3 is radical 3 over 2. Sine of pi over 6 is 1/2. This times 2. So this is going to be radical 3 minus radical 3 over 2. Which is 4 times 2. 8 over radical 3. Yeah, because this denominator just turns out to be radical 3 over 2. Invert and multiply. So I think the rate of change at pi over 6, theta equals pi over 6 is 8 radical 3. How do we get my point? Now I need a point xy. Well, that's just going to be at pi over 6. R sine theta, R cosine theta. All right, so what is R? So we got to find R at pi over 6. Multiply it by sine of pi over 6, we get y. Find R at pi over 6, multiply it by cosine of pi over 6, and get x. And that'll be our ordered pair. So then I'll have my rate of change, and I'll have my point, and I can write the equation of the line. Okay, so can you see through to the finish? So that's kind of lots of algebra, or lots of arithmetic, actually, trig. Questions on that? So I did the dy dx, and I'd leave it to you to find x and y. R is going to be 2 times sine of 2 times pi over 6. Use it in both of those formulas there to get your x and y coordinate. You got the point and the slope, or the rate of change. You can write the equation of the line. All right, any questions? So we talked about it last time, but this idea of when does the curve get furthest to the right, or furthest at the bottom, or the furthest to the top, really important, okay? And we're going to use our derivatives to think about that, right? So the meanings of our derivatives will give us, pinpoint those locations where we're furthest to the right or furthest to the left. So make sure you know that. And there are lots of web work problems testing you on that. Okay, can we go on? Other questions about the homework? So let's talk about area. In polar coordinates. Oh, Clara. Forgot. How's it going? Okay, so if you're ever kind of stuck, especially on that first page, or go to the class video and watch the animation. The animation is really important that you always have this clear visual in your mind of what's going on. Don't get so bogged down in all the details of calculations that you lose track of what's really what's happening here. Okay, so without going into detail on any particular question, are there any general questions about the project due Friday? So hopefully you're at least half done. You've really thought about it and worked at it. Don't save it till tomorrow night. You can't do it in one night. But any questions about it? Yes, ma'am. So it really kind of doesn't matter. So it's, I don't remember how the project actually frames it. Does it say whether? Yeah, so just as long as you explain what you're doing, it's really the same thing. I mean, so if there's no fence here, then Clara has the exact same opportunity to walk and graze underneath as she does above, and kind of everything's multiplied by 2, okay? Or you can just say, just assume that there's a fence here. Just assume there's a fence, and you're just worrying about the top half. It makes really no difference to what you have to do in the project. So as long as if it doesn't specify it in the question, just be clear how you're thinking about it, and it's fine. So yeah, it's really the same thing, whether she can keep going and have the symmetric path underneath or not. There's no additional mathematics to it. Just be clear in your explanation. Other questions? Yes? Yeah. So don't print that out and scribble on it and have it be crumpled. Yeah. So if you want to kind of redo it with a word processor and have all your answers typewritten, that would be great. Yeah. So what would you turn into your boss because you're getting paid for it versus what would you kind of be ashamed of to turn in? Okay. Does that help? Yeah. Okay. Other questions? Yes, sir. Sure. Yeah. So you can still, you don't have to type it to qualify for extra credit, but it should look really good. Yeah. But typing it would take that question off the table, right? Other questions? Okay. So yeah. So we're available for help. We're not going to do it for you, but we'll definitely listen to your thinking and try to ask you questions and get you going in the right direction if you're needing help. So don't hesitate to ask. And if it's a kind of a shorter question, you could even email it. Okay. But if it's a discussion type question, then just find one of us, and we're happy to talk with you. Okay. So now let's do it. So the idea with area, so we have some function, but as theta changes, r changes with it, right? So depending on some relationship between r and theta, we get, given any theta, we get some value of r, and if we take all those collection of points, we get a curve like this. So before we do this, I want to just, there's one thing we need, a little a tool that we need for this. So just, how do you find, what's the relationship between angle on an angle of a circle, call it alpha, and arc length, s? So actually, the definition of radian measure is that alpha actually equals S. That angle measure in radians just comes from the length of S. If you use the right unit to measure S in. Measured in what unit do we get this angle theta directly from arc length? In radius lengths, right? So if you use the radius length as your measuring stick, and you count off how many radius lengths this is, that's what alpha is. That's what that angle is. It's how many radius lengths of arc length get cut off by the rays. So now if we want S, not in terms of the radius, but say in whatever the units the radius is measured in, feet, miles, inches, then what is S going to be? So alpha is the number of radius lengths, and then if the length of the radius is r, then how long will S be? Yeah, so it's going to be, so alpha. So alpha is the number of radius lengths, r is the length of the radius, so how long is that? So it's theta number of r's, right? S is theta number of r's, of arc length. So S equals, or alpha, guys, alpha, sorry. So R alpha, right? So the radius times the angle measure in radians gives you the arc length. So we're going to need that for this. Okay, so the idea is that we're going to have some change in angle. So say from theta 1 to theta 2. And as we change from theta 1 to theta, that's our independent variable, right? So as we change from theta 1 to theta 2, with r as this boundary, that's going to define an area, right? So as theta changes from theta 1 to theta 2, we're going to get there is some area that gets swept out, right? There's some area that gets swept out. So how can we find that? So back to our geometry unit. What was our way of calculating an area? Yeah. Before that. Right, so we want a bunch of little pieces, or a typical strip, right? So now what's a typical strip going to be like in polar coordinates? What's a typical strip going to be like in polar coordinates? So like this. So that would be if it was based on like a small change in r, right? But we want it to be a small change of our independent variable. So if we have a small change in, what's our independent variable? Theta. What does our typical strip? Lots of hands up. I think I saw Seth first. Okay, what were you gonna say?
I was going to say more like small triangles.
Okay.
I would say like a small, like how you have the lines to show where theta is. It's just an infinite number of them.
So what's one of them? What's the shape of one of them? Yeah. Sector. Okay, yeah, so I think, so somewhere in here we could draw just a little change in, it didn't work out. It was going so good. All right, let's try again. Yeah. Not the worst, not the best. Yeah, so imagine those are straight, right? So a little change of theta, it doesn't give us a rectangular strip anymore. Why? Because it comes to a point, right? All angles of theta come to a point here. So what is the shape of that? So some of you said it. So like a sector, like a really thin sector, or a triangular region, or you said a cone. Cones are three-dimensional, but you had the right image in mind. Yeah. So this is going to be our delta A. So this shaded in like this. Hand doesn't go where you want it to go. Okay, not so this thing is going to be our delta A. And it's a triangle, not a rectangle. So it's a typical triangle, not a typical. So what's going on here? So what is the area of a triangle? 1/2 base times height. So we're going to use as the base, this is going to be the base over here. So let's start with the height. What is the height of that triangle? Right, so that whatever, at that theta, whatever r is. Right, so whatever r is, the distance from the pole out to the curve, the height of the triangle is r. That went better, so that's, the height is r. So now the base. The base is this little distance right here. It's a length. So is it d theta? Is d theta a length? No, okay. So how are we going to get the length? And so this right here is the base of the triangle. So the height is r. It's from the pole out to the end of it. So that base of that skinny triangle is what? Arc length. So what's the arc length? How are we going to calculate that arc length? Radius times alpha, right? So this is where our tool comes in, right? So it's going to be whatever the radius is to that arc length times the angle. So what is the distance? What is the radius? It's just r. And what is our angle? Delta theta. This is a little change in theta. So that makes B what? R delta theta. And then we have the 1/2. So our delta A equals 1/2 base, which is from our arc length, it's going to be R times the little change in angle times the height, which is also R. So what do we get? We get 1/2 R squared delta theta, and that's our delta A. So then what is the area of the whole thing? So can you do it? Write the area of this whole thing starting at theta 1, ending at theta 2. So that's the area of a typical triangle. Area of a typical triangle. And now I want the area of that whole, the black crosshatched or black shaded region. Okay. So what, any volunteer? Say yeah, somebody here. I know Griffin's got it, I know Jacob's got it. Somebody new? Yes, sir? Okay. So now it's d theta, right? Yep, so now we're going to sum up, right? We're going to sum up all the typical little triangles as they get really super thin, like slivers, right? So these sliver triangles get really small as delta theta gets small. We're going to add up all those typical triangular slivers starting at theta 1 to theta 2. So that is our generic, so that's our generic formula for area in polar coordinates. Again, our typical element now is these triangles, right? So it was all based on the area of a triangle, 1/2 base times height. Okay? But then what is R? Where does R come from? What is that? What's the radius? What is R? What is it? It's this function of theta, right? It changes with theta, right? So this is going to be whatever our expression is that gives us this curve, right? Whatever expression of theta gives us this curve is going to be that, and that gives us that entire integral in terms of theta. Right? That gives us the integral in terms of theta. Okay. Any questions on that? So that's just developing the formula for area. So we'll do an example here. Any questions on that? Does it make sense? Don't hesitate to ask. It's okay. Can I erase? Okay, so let's look at can you sketch each of these in the first quadrant? Sketch each of these in the first quadrant. 5 cosine theta minus 2, cosine theta plus 1. Only from 0 to pi over 2. It's good practice. So 5 cosine theta minus 2. And cosine theta plus 1. Just do the first from 0 to pi over 2. Sketch both of those. Okay, see how you did? Here you go, see how you did? Is that what you got? So which is which here? The blue one is function f, right? And the red one is g. Any questions on sketching? So we've done lots of these. Hopefully you're making more sense, getting a little quicker. So before we talk about areas, which we'll do on Friday, so what's going to be important is what are the coordinates of this point of intersection, and then what's happening here? So what's true about this point right here? Can we identify what's going on, and then any values associated with it? And then what about this point right here? Did you have points of intersection in the web work? No? Okay. So for the last web work for area, you will. So points of intersection. So how can I nail down what, say, the coordinates of that point is, whether r theta or xy? Okay, set what equal to each other? What's equal there? Okay, and those f theta and g theta are values of? What is that a value of? R, right? So yeah, so we want the angle theta such that r's are equal. R's are equal, right? So at some point here in between 0 and pi over 2, there's a theta value for which r's are equal, and so we'll set this r value of g theta equal to f of theta. So by setting those equal, we're saying what value of theta gives us the same r, right? We're saying what value of theta gives us the same r. So you get 4 cosine theta equals negative 3? No, 3. 6, 4, that's right. So I subtracted cosine theta from both sides, I added 2 to both sides, and then I switched sides. So cosine theta equals 3/4. Is that a standard angle that we know? 3/4? No, not quite. So we'll just write it as inverse cosine of 3/4. And then to get the value of r, what's the value of r? So if cosine theta is 3/4, then we're talking about a value of r of 1 3/4, right? 1 3/4. Cosine theta is 3/4, then this point is 1 3/4, comma, cosine inverse of 3/4. That's the polar coordinates of that point. But for the purposes of defining areas, we're really most interested in that angle, right? That angle as a starting or stopping point for defining some regions. Does it make sense? Okay, what's happening here? Okay, you said where the r value switches from positive to negative, and therefore the r value is 0. So this is r equals 0, and which r are we talking about? F, right? So we're talking about there's some angle for which r is 0, or the value of f is 0. So what do? We say, well, we know r for f is 5 cosine theta minus 2. So this is going to be cosine inverse of 5/2 or 2/5? 2/5. Right, cosine theta equal 2/5. So this angle is where they intersect. This angle is that angle measure for which f hits 0 and goes negative, like you said. It turns from positive to negative. Okay, so we've kind of set up a situation here. There's lots of different regions we can talk about defined by these curves in order to find areas of, and we'll do that on Friday. So